nanoHUB-U, online instruction.
Welcome back to Unit 3 of our course on quantum transport, and this is Lecture 4. Now, if you remember, in the last lecture, we talked about this general way of finding the self-energy. And this expression we obtained was this tau g tau dagger, where this g is called this surface Green's function. Now, to use this formula, of course, you need to have a way to calculate this surface Green's function, and that's what we'll talk about in this lecture. Now, you'll notice here this E plus I eta minus H inverse. So you might say, well, it looks straightforward. You just take that matrix and invert it. Oh, by the way, just to remind you again, H is this matrix which describes your contact here. And so in general, it's a very big matrix, right? It could be 1,000 by 1,000, for example. And of course, as I mentioned earlier, just for clarity, I was being a little sloppy. I should have written E plus I eta times the identity matrix. An identity matrix that's of the same size as H. But that, as you know, we have not been doing, just for clarity. Okay. But the thing is that when I invert this, you might think I'd get a 1,000 by 1,000 matrix if you had 1,000 basis functions for your contact. But what we're interested in is only the surface part of it. That is, you have this huge matrix, you just want the surface part, not the whole thing. Right? So the size of this matrix G is really equal to the number of basis functions at the surface. That is, the surface of the contact that gets connected onto the device. So that's what we need to evaluate. And that's why it's not a straightforward inversion of a matrix, because you are inverting a huge matrix and then just looking at the surface part of it. Okay. So how could we do this in general? So let's assume your contact, as before, you could think of as a 1D chain where each element of the chain represents that entire column. So if a column has 9 points, that alpha is a 9 by 9 matrix. Similarly, the beta is what connects one column to the next, and that again would be a 9 by 9 matrix. So in general, you could always represent this structure like a 1D structure, but each element being a matrix representing the entire column. Now, consider now a contact which has a total of, say, n columns, but then we think of n minus 1 separate from the last one. So think of it like this surface is this alpha, which is connected to the rest of the contact, and the rest of the contact is this n minus 1 columns. So overall, it's a contact with n columns, which I've written as Hn. So you could write E plus I eta minus Hn, and if you invert it, there would be a big matrix corresponding to all n columns, but you just want, of course, the surface one, the last one. So one way to find this would be to kind of treat this as your device and the rest of it, the n minus 1 columns, as your contact. Because then, you see, you could represent this entire thing with a sigma, with this self-energy. And what would I use for the self-energy? Well, it would again be this tau g tau dagger. And of course, tau is the connection from this device to the contact, and that connection is beta dagger. So the tau is the beta dagger and tau dagger is beta. So you could write the self-energy for these n minus 1 columns in this form, where this G is the surface Green's function for a contact with n minus 1 columns. Now, how do you find that? Well, that we'll see. But supposing you knew it, supposing you knew the surface Green's function for n minus 1 columns, then you could write the self-energy in this form. And using this self-energy, you could then write this inverse as, you see, this point, this is my device, its Hamiltonian is just alpha, and for the rest of it, I'll just write the sigma. So E minus H minus sigma inverse. That should give me the Green's function for this surface. See, and that should be exactly what I'd have got if I had inverted this entire thing and got that. So straightforward approach would be take that entire n things and invert it, and then look at the surface one. But alternatively, you could just take the surface one and treat the rest of it as if it's a contact to that one. So treat it through a sigma. So the point is then that the surface Green's function for a contact with n columns is related to the surface Green's function for a contact with n minus 1 columns through this relation. See? And you could invert it to write it as Gn inverse is equal to E plus I eta minus alpha minus this sigma for the n minus 1 columns. So what you have here is what you might call a recursion relation, in the sense that if you know the surface Green's function for n minus 1 columns, you could use this to find what it is for n columns. And so this is a process you could do recursively. That is, you start out by saying, okay, I know the surface Green's function for a contact with just one column. That's easy, because if it's just one column, it's just E plus I eta minus alpha inverse. So that would give me the Green's function for just one column. So I could put that in there and get the Green's function for 2 columns. Okay, then you take the 2 columns, put it in there, and you get the 3 columns. Put it back in there, you get 4 columns, and so on, right? And when a contact is large enough, then you'd get to the case of an infinite contact, when you find that if you take, say, 1000 columns and you add one more column, it doesn't change much. It essentially has converged. So the converged solution would be when that G is equal to that one. So in a way, you could say that the actual surface Green's function that we are looking for should satisfy this equation, where the G for n minus 1 and the G for n have converged onto the same value G that we want. And this you could turn around and write in this form as well. What kind of looks like a sort of a quadratic kind of equation for G. You know, it involves a term with G, a term that doesn't involve G, and a term that involves G inverse. Kind of like x, 0, and 1 over x. So it's an equation in G. But it's a matrix equation, of course. These are all matrices. So this is the equation, you know, this one or this one, that you could solve in general to find the surface Green's function of any contact, described by a 1D chain like this with alphas and betas. So once you have the alphas and betas, point is to solve this. So one thing you could try out is that, well, for a simple 1D chain, you know, where these alphas and betas were not matrices, you know, where you had just no columns this way, it was just a single point in this direction. In that case, we had an answer in unit 2. We had the simple answer t to the power I k a. So now that we have this general high-powered method for finding G, would we get the same answer if we use this? That would be a natural thing to check. So let's do that. So we have consider the 1D chain, where the alpha is just the number epsilon, which is this diagonal element. And the beta is another number t, which is the nearest neighbor coupling. And as you know, the dispersion relation would be E equals epsilon plus 2t cosine Ka. And to this we have added the small imaginary term that I had mentioned before, the one that you add to describe this physical fact that electrons flow away from that contact. Okay. So you'll have this relation. Now, if you substitute alpha equals epsilon and beta equals t in here, you'll get, you see, beta dagger beta, that's just t squared. So it's t squared g minus this quantity alpha is epsilon plus G inverse is equal to 0. Now, if you multiply by G, you have this quadratic equation. And now it's of course a normal quadratic equation. In the sense we are talking of numbers, not matrices. In general, what you have is a matrix quadratic equation. But here's a simple quadratic equation, so that you can solve straightforwardly. As you know, there is a simple way to write the solution to G. It's negative of this coefficient plus minus square root of this thing squared minus 4 this times that. So that's this divided by twice that coefficient. So this you can simplify a little bit. You have a 1 over t in front. The 2t cancels this 2t squared. And you have cosine Ka plus minus square root of cosine squared minus 1. Which is like I sine Ka. Because 1 minus cosine squared is sine square. And this is cosine square minus 1. So you pick out a I. And this, if you remember your trig identity, that's what you can write as e to the power plus minus IKA. So this would then be the surface Green's function. So how would you find the self energy? Well, self energy would be this tau g tau dagger. And in this case, again, if it's a uniform chain, the tau is same as beta, it's equal to t. So you have t squared times g, and that gives you t e to the power plus minus IKA. And if you look back, that's exactly the answer we had back in Unit 2, where we were using much simpler arguments and using just a 1D chain. But we had to impose this boundary condition that you have an outgoing wave in the contact. Now, one point I had made in that context is that whether you look at sigma or whether you look at G, they should have, their imaginary part should be negative. Because this imaginary part of G is like the density of states, which physically needs to be positive. So I guess the negative of the imaginary part is the density of states. And so that needs to be negative here. This imaginary part of G needs to be negative. Imaginary part of sigma needs to be negative in general. Now, how did we ensure that when we were doing this elementary method back in Unit 2? Well, we said that when you come to the contact, you only take an outgoing wave. And an outgoing wave, of course, depending on the sign of t, would be either e to the power plus IKA or would lead to e to the power minus IKA. Depends on which has this correct sign of the group velocity. So this is the argument we had made earlier. Now, in this context, you might wonder, how would we select the correct sign? And that's where I'd like to make the point that in this case, you'd get the correct sign automatically if instead of solving this equation, which is what we just did, the quadratic equation, if we solve the original one. The original one, you see, this is a quadratic equation, which we got by multiplying this one by G. But supposing we hadn't multiplied it, we just started from here. Then one way to solve this equation is iteratively. That is, what you do is, you say, okay, let's turn it around and write it in this form. G inverse is equal to e plus I eta minus epsilon minus t squared G. And then we say, okay, if you drop this term, we'd have your first guess solution for G, which would be G inverse would be Z. And so if you substitute that back in here, you'd get Z minus T squared over Z. Because, right? So that's like you're saying, well, my first guess for G inverse is Z. So if I put that back in there, I'd get this answer. Now the next step in the iteration is where you'd say, no, we use this for G. In which case you'd get Z minus T squared divided by that answer. And now you can go on. Next iteration, you'd have additional terms like this, continued fraction essentially. But this you can do on a computer. That is, start with a guess for G, which is the inverse of, which is 1 over Z. Put it back in there, whatever you get, new one, put it back in there and keep doing it. So you could solve it this way. And the point is that if you did that, you'd automatically get the correct sign. This you can kind of see because, you see, if you looked at the imaginary part of G inverse, that's positive, because for the first guess at least, because this Z has a positive imaginary part. And what you can check is that as you add these new terms in your iteration, each one has a positive imaginary part. And so as long as you have this E plus I eta and you start from this first value, which is 1 over Z, which has a positive imaginary, Z has a positive imaginary part, the imaginary part of G inverse after many iterations will still have a positive value. And so if you went on, the imaginary part of G, which is the inverse of it, would be less than 0, which, as I had mentioned, is something that's physically important, because let's say the negative imaginary part is what's like the density of states, and which needs to be positive. And the point I'm trying to make is that if you solve this equation iteratively, you automatically get converged to the right solution, the one with the correct sign. Now, in general, so what we have just looked at is, of course, this special case of a 1D chain. And of course, if this is the only problem you are interested in, then you didn't need this method. We had a satisfactory, much simpler method back in Unit 2. The reason we are doing this one is, this is general. This would work in complicated problems, as long as your contact can be represented as a chain with matrix elements like this, which represent an entire column, which are connected by matrices. So as long as you have a problem like this, you could always find the surface Green's function as well as the self-energy using this method. And how would you use this method? Well, in general, you would have this matrix equation that you need to solve, which you could solve iteratively. Just the point I had made, that you write G as equal to this quantity inverse, and if you start with some guess for G, so the first guess is you drop this term. Whatever you get, that's your first guess. Put it back in there, invert it, get your second guess. Well, put the second guess back in there, invert it, get your third guess, and so on. And it usually would converge reasonably quickly. This depends on the value of the I eta that you choose, and it's meant to be a small number. If you use a very small number, then you'd have to iterate many times before you converge. If you use a slightly bigger number, it would converge faster. But the point is, this iteration then gets you this surface Green's function, and the value it converges to doesn't depend on the precise value of eta that you use. It only affects how long it takes you to converge, that's all. And at the end of it then, you'd get the G, and once you have the G, you can calculate sigma. So overall then, what you have managed to do is, we now have a general method for finding the self-energy, which involves the surface Green's function, and what we just described to you is the equation that you have to solve to find the surface Green's function. So that's kind of what we did in the last 2 lectures. And what we'll do after this is, we'll look at a couple of examples where we apply this method. These are examples I've chosen because you couldn't have done it using the old method, the one that we discussed in lecture 2, because you would not be able to diagonalize alpha and beta simultaneously. But numerically, you could use this method easily once you have the alphas and betas. So in the next lecture then, we'll look at one of these examples involving graphene, and then later we'll talk about another example in a conductor in a magnetic field. Thank you.